Hello, hello, hello,
Yeah, that's fine. I just need
hello.
to make sure.
Okay. Maybe, maybe, yeah, I'll email out the link. Okay. Oh, wait. Can we ask Albert to sit closer here in case there are tech problems?
Am I good here or should
Oh yeah, that's totally fine. I just,
you can just
you
wear
know,
this? Because
Albert. Yeah. Wait, so are we currently recording or only live streaming?
Or like,
Okay. So I guess should we record? I guess we can start recording once Selena starts talking.
I don't think we need to record, right? Like, it'll be, like, YouTube will save it for us.
Yeah, you can, or you
Hopefully.
can
It saved the last one.
Okay. I did click record for the last
Yeah, so I
one.
think it's gonna have to go in.
So I guess we can do record just in case.
Okay, that was awesome.
Yeah, because well, uploaded it straight to YouTube. I, or at least didn't see it download to.
No, when you start recording here, not saving it locally.
Okay.
YouTube
So
just saved everything you.
okay. So apparently there was no storage. Because I did record it.
What is this?
That one. Hello? Hello?
Sorry, we're just testing mics. We'll start in like a minute. It's so quiet. It's okay.
Wait, you need your slide deck.
Yeah, I need this. Okay. Wait, I can just use that, right? The whatever this thing is. Oh, and to like control it. Is this one?
Wait, are you standing here? We'll use the podium mic instead.
Okay, yeah.
Yeah, probably in 20 minutes or so.
Hello. Hello. Okay. I'm saying here. I need to read the slides.
Okay.
Yeah. Thank you. Should we start?
Yeah, just 1 second.
Okay.
Oh, also, so if you want to show like pretty pictures, really the only lighting settings are like lights completely off or lights like this. So, so do you want us to turn the lights on? Like, oh yeah, you'll be able to see them here and just to make it more visible. Yeah, unfortunately, that's I think the only. I guess your face would be illuminated by the monitor. Yeah, we can try it. Lights off, and then we can turn it back on. Actually, should we turn the lights off now, or should we wait until?
Up to you. I don't really care. Yeah, announcement and stuff, right?
I guess people are still maybe funneling.
Yeah, people are going to come.
Yeah, we can get started now.
Yeah, okay. All right, hi everyone. I'm at Audible. Hi. Welcome to the second to the last astronomy public lecture series of the semester. We have a whole night of fun waiting for you. But before we start, can you scan that QR code or go to the URL to sign in? There will be a raffle on whoever signs in, and the prizes are quite cute. I personally want them, but I'm not qualified, unfortunately. So take advantage of the raffle by signing in. The link is also on the board, just if you are not able to get it in time before we switch slides. Everything here, questions, and also feedback form, and also restroom, and also the next event date. All right, 3, 2, 1, switching slides. Perfect. Welcome again. So tonight, we are going to start with astronomy trivia, as always. So that will be 5 problems of multiple choice. Whole lot of fun. See if you can get some right. Then we are going to hear from our amazing Shifra on the talk about zombies in the sky and also what happens when stars die. So if you were here last public lecture series, we had a question about explosions, and unfortunately last week was not about explosions, it was about JWST, but this week we have explosions. Lastly, we don't know yet, so right now the cloud coverage is 50%. We are going to check in another time later in the talk to see if we can do observing. If we can, that'll be the first ever observing of the semester, and if we cannot, that's the universe telling us that our speakers are way too interesting and they want to hear more from them than for us to look at them, I guess. Okay. So, are we ready for trivia? Yes. Okay, perfect. Question 1. When a massive star cannot produce enough fuel to hold itself up against gravity, its core collapses, yielding a violent supernova explosion. Roughly, what is the minimum amount of mass a hydrogen-fusing star must start with to trigger a supernova later in life? A, 8 times the mass of the sun. Raise your hand if you think that that's the choice. Sorry? Oh. Maybe. Choice A, Team A. No one. Team B, 15 times the mass of the sun. More people. C, 90 times the mass of the sun. That's really heavy. D, 200 times the mass of the sun. No one again. Okay, there's some. The correct, it's actually weirdly light. It is 8 times the mass of the sun. All right, question 2. In 1987, a supernova explosion was observed in a nearby galaxy known as a Large Magellanic Cloud. This supernova, called SN, you guessed it, 1987A, is one of the best studied stellar explosions of all time. Roughly how far away from us did SN 1987A occur? Team A, 200 light years. 200 times the distance that light takes to travel in a year. All right. B, 2,000 light years. A bit more. C, 20,000 light years. D, 200,000 light years. Okay, a bit more. Which one is it? Final answer D. It is quite far away. But if you are ever in the southern hemisphere and the night is clear, you might be able to see the Large Magellanic Cloud with its like tune, the small one, at night. Question 3. Smaller stars like our sun end their life as white dwarfs, which are small, dim, and dead, but very compact. Stars around the size of the Earth. Wait, shoot. What am I reading like? Okay. Small stars like our sun end their life as white dwarfs, which are small, dim, and dead, but very compact. Stars around the size of the Earth. What is the density of a typical white dwarf compared to that of Earth? A, 100 times the density of Earth. Okay, no one. B, 1,000 times the density of Earth. Okay, a bit more. C, 100,000 times the density of Earth. Okay, a lot more. All right, D, we're getting really dense. 1,000,000 times as dense as the Earth. Okay, a bit more. Which one is it? It is 100,000 times the density of Earth. So you can probably imagine, like, our sun shrunk down to the size of the Earth. It is going to be very dense, but probably not as dense as 1,000,000 times dense as Earth, because that would be crazily dense, and we will learn from Shifra what that becomes. Okay, the second or last question. You still have chances. The periodic table lists 118 elements, many of which are produced by dead or dying stars. Which of the following events can produce calcium, which is what makes our bones our bones? A dying low-mass star. No one? Okay. B, exploding high-mass stars. So heavy stars exploding when they die. C, exploding dead stars. We learned about white dwarf, I think 1 question ago. All right, no one. D, both B and C. The correct answer is both B and C. So we need to thank our explosions to make bones. Alright. The interior composition of neutron stars, another class of dead stars, remain a mystery. The New Star Telescope seeks to probe the internal state of neutron stars. What type of radiation is New Star designed to see? A, optical light. That's the color that you see. So I'm wearing like a navy blue shirt or skirt. That's the ray that the telescope sees. No one. B, infrared light. That's the heat. So if you walk today, it was very hot. It came from the infrared radiation of the sun. Okay, a bit more. C, X-ray light. What you see in doctors to have your bones checked. All right, a bit more. D, ultraviolet light. What do you wear sunscreen for? Bit more. Okay. It's actually C. We see an X-ray light. So, I guess this is probably not scientifically accurate, but you know how X-rays can see bones of skeletons? It's probably we use the same X-ray light to see dead stars. That's how I remember it. It's not scientifically accurate. It's just what I came up with. All right, so that concludes the trivia portion of tonight. Hope that the questions were entertaining and fun. This is another chance for the QR code for the welcome. We are going to have a raffle for the people who sign up, and the prizes are very cute. So do make sure that you do this. It's also going to help us a lot to host future events and to know what methods we can best advertise to you with information. Okay, sorry.
No, you can keep talking.
Oh. Wait, I can't. I need to go to the next slide.
Oh, you wanted to do I thought you wanted to do this later.
Yeah.
Okay.
Wait. Oh. So now I'm going to introduce Ryan, who is the lead organizer of this series of event, and he is going to make a few announcements and introduce our amazing speaker of the night. Let's welcome Ryan.
Okay. Hey everyone, thank you all so much for coming out here. My name is Ryan Golant. I am a third-year PhD candidate in the astronomy department here. And I am super excited to welcome all of you here for our second to last astronomy outreach event of the semester, as Selena already said. I'm going to give you one last chance to fill out the, one last chance to fill out the sign-in form, because, as Selena said, there's this quid pro quo. We have these cool little astronomy trinkets, but we need your data in order to give them out to you. So take one more minute to scan the QR code, fill out the form. Okay. So thank you to all of you. Thank you especially to Selena, who put together the trivia, who put together those fantastic flyers that were sent out to all the listservs, were posted on Instagram, on Twitter, on Facebook, all of that. So huge round of applause to Selena. And I'd also like to thank Matthew Wernicken, Albert Jing, and Aiden Cloud for also helping organize tonight's event. I can't actually see anybody, so I don't know where they are, but I sense that they're here, hopefully. Right, okay. So we will be, So unfortunately, our semester is coming to a close pretty soon, which means besides this night, this event tonight, we only have one more event on April 28th. We'll be hearing from another grad student, Ben Cassess. But don't despair. This is not the end of public astronomy. We might be doing some programming over the summer. That's still in planning. We will be back in the fall with many, many more public talks, and hopefully a lot more public stargazing. Hopefully you signed in. We'll be raffling off little trinkets from Startorialist, which, if you're not familiar with, make a lot of really cute astronomy-related trinkets, little plush toys, other fashion accessories. So I'm going to go through a few announcements before introducing Shifra. Actually, we'll be talking a lot about the deaths of stars. I think my first announcement is something that may be on a number of your minds. If you're coming to our events before the pandemic, you may have been wondering why we haven't been using the roof dome, the observatory on the top of Hupin. Many reasons. A big one is that the dome has been more or less broken for the past year and a half. But recently it started undergoing repairs, and so hopefully we'll have a fixed dome by the end of April. So fingers crossed that we'll be able to use the dome for observing on April 28th. So I do know we haven't really gotten to observe yet this semester. It's been cloudy every day. Maybe we'll get to observe tonight. Who knows? But for all the gamblers in the audience, we all know that the sunk cost fallacy is fake. So we'll just keep doing what we have been doing until we get a win, which will be at some point, hopefully April 28th. Another announcement. The Northeast Astronomy Festival or Astronomy Forum is happening this weekend. It's an expo mainly for amateur astronomers, but there are talks from former astronauts, from working astrophysicists, from people who have worked on James Webb Space Telescope. It should be a really fun thing. So if you're interested in that, you can check out the website at naafexpo.com, and that's this weekend. And in other news about fun astronaut talks, the Columbia Space Initiative next Friday is hosting a Zoom call with astronaut Woody Hoberg, who is actually currently on the International Space Station. So if you're interested in seeing or talking to an astronaut who's currently on the International Space Station, you can scan that interest form. There's currently a lot of interest for this. Or you can come talk to us afterwards. Matthew Wernigan, who is maybe somewhere here, maybe not, is in charge of this. So yeah, so I think I've said enough. Now I'm extremely honored to introduce our main speaker for tonight, Shifra Mandel. So Shifra is a fellow third-year astronomy PhD candidate, along with me. We're actually in the same office together, so I know her quite well. I know she's a fantastic scientist, and she also has a very, very interesting backstory or biography. So Shifra actually grew up in a very Orthodox Jewish community, where the universe was considered to be maybe a few thousands of years old. So Shifra didn't actually encounter modern astronomy until she was nearly an adult. But once she did start learning about the stars and about the universe, then it immediately drew her in. So in 2014, Shifra got her GED. Then she started out as an undergraduate at Columbia in 2015, where she earned a bachelor's in physics. Then she spent 2 years doing just astronomy research through the Bridge program here at Columbia. She did 2 years of astronomy research with Professor Katherine Johnson. And then after that, she became a full Columbia Astronomy PhD candidate, or PhD student, and a National Science Foundation Graduate Research Fellow in 2020. So she's been at Columbia for a while, doing a lot of astronomy research. And so during her time as an astronomer, Shifra has co-authored 7 papers, which is very impressive for her stage in her career. And one of those 7 papers she's the first author on. Another of those 7 papers was published in Nature Astronomy, which is a very highly regarded astronomy journal. The paper was about X-ray emission from Jupiter, which seems very cool, and I'm sure she'd be happy to answer any questions about that after her talk. So Shifra's work is mainly in X-ray astronomy. She's used instruments like NuSTAR, which we mentioned, and XMM Newton to study dead stars, which she'll be talking about a whole lot more in the next few minutes. But first, I do want to highlight one of Shifra's recent non-science hobbies, and that is fostering this little cat, Mimi. So this is Mimi. This is also Mimi. And this is also Mimi. So it's not astrophysics, but I feel like fostering a cat is a science in its own right. And maybe, I think it's an open question whether X-ray astronomy is more or less difficult than fostering a cat. So I've definitely said enough. So without further ado, give a warm welcome to Shifra Mandel.
All right, cool. Thank you, Ryan. Well, thank you all for being here today. I'm going to be talking about dead stars because I believe that they're the best kind of star. And after my talk, I'm sure you will all agree with me. Actually, scratch that. The absolute best kind of star is a zombie star, which is a star that died and was then revived and is now feeding on anything and everything that's unfortunate enough to come close to it. Arguably the most popular kind of dead star, and for good reason, is the black hole, which is pictured here on the screen in high definition. Now, if you're among the people who think that humanity is in danger from black holes, first off, I would just like to say, you've got nothing to worry about. There are many, many things that we can and should be worried about, including but not limited to global warming, environmental pollution, growing inequality, extremist ideologies, the opioid epidemic. One thing you should definitely not be worrying about is black holes. Now, what is actually a black hole? A black hole is a kink in space-time with a singularity at its center, a point with infinite density and no volume. It's so massive and so incredibly dense that space-time itself is distorted beyond our comprehension. A black hole doesn't have a regular surface. Instead, it's surrounded by a boundary, which we call the event horizon. Once this boundary is crossed, there is no returning. Nothing can escape from inside the event horizon, not even light, hence the name black hole. In a certain sense, as paradoxical as it sounds, black holes are really very straightforward objects. This is something known as the no-here theorem. Because no information can reach us from beyond the event horizon, we don't have to worry about a lot of the details on the inside of the black hole, like, for example, the composition. What is it made of? It actually doesn't matter when we want to study a black hole. There are only 3 properties of a black hole that completely describe it. The first one is its mass. The gravitational force of the black hole is going to depend on its mass. The more massive it is, the stronger the gravitational force. And also, the more massive it is, the larger the event horizon, that threshold of no return. The second property of a black hole is its spin. Virtually all celestial objects, from stars to planets to galaxies, have a spin, and black holes are no exception. Black holes spin as well. And the third property of a black hole is its electric charge. However, we can generally assume that the electric charge is neutral. Black holes may have some electric charge when they are formed, but they lose any electric charge to the surrounding matter very quickly. This leaves us with just 2 heres, or 2 properties that matter to our measurements: the mass and the spin of the black hole. Now, how do these magnificent beasts come to exist? So if we want to answer that question, we have to first take a step back. There are 4 distinct types of black holes, and each one has its own unique properties and mechanism of formation. The first kind is the supermassive black hole. All galaxies have one. Our very own Sagittarius A star, which is the supermassive black hole at the center of our Milky Way galaxy, which is pictured here on the right, has a mass that's equivalent to more than 4 million suns combined. The only other black hole that was ever imaged in the massive galaxy M87 has a mass of over 6.5 billion suns. So the moniker supermassive is very appropriate. So that's one type of black hole. The second type of black hole is the intermediate mass black hole. As the name suggests, it's not quite as massive as the supermassive black hole, but it's still pretty formidable. You would not want to come across one of these babies in a dark alley. And the third kind is called a stellar mass black hole. It can be anywhere between a few times the mass of our sun to dozens of solar masses. This is the kind that I will be focusing on in the rest of the talk. So stellar mass black holes are the remnants of massive stars that exploded in a supernova, as was mentioned earlier in the trivia portion, like the one shown in the image here, which happened in 1987, as was also mentioned in the trivia portion. And finally, the fourth kind is the primordial black hole. Hypothetically, these tiny black holes may have formed in the very early universe, shortly after the Big Bang. They haven't been observed, but we currently don't really have the capabilities to detect their signals, so stay tuned. But they could be all around us, and if that makes you nervous, I promise they won't hurt you. Back to our question, how are black holes formed? So speaking now about stellar mass black holes, the short answer is they are formed from the remnant of a massive star that died and collapsed in on itself. All stars form out of clouds of gas and dust that collapse in on themselves. That's how it starts out. Like most of the matter in the universe, stars are made primarily out of hydrogen gas. And if the conditions are right, meaning the temperature and the density and the pressure, then the core of the star will ignite and hydrogen atoms will start fusing into helium atoms. This is called stellar nucleosynthesis. When this nuclear fusion process begins, that is when a star is properly called a star. And all stars start off like that. Now, even though every star starts off the same way by fusing hydrogen into helium in their cores, different stars still undergo very different end stages, as this diagram here illustrates. Another thing that all stars have in common is that while they are alive, meaning while there is nuclear fusion ongoing in their core, the pressure released by the fusion process keeps the star stable because it balances out the gravitational force of the star that's pulling inwards towards the center. That's how a star is kept in equilibrium. Well, once the star runs out of fuel, the nuclear burning ends and the gas pressure is no longer available to fight against gravity. So the star begins to contract from the immense gravitational pressure. Depending on the mass of the star, there may be a massive explosion called a supernova. This happens for the very massive stars, those that are around 10 times the mass of our sun, or even bigger. A supernova is a very rare event because compared to sun-like stars, those very massive stars are pretty rare. The picture on the right here shows the Crab Nebula, one of the most famous X-ray sources, which is the remnant of a massive star that exploded thousands of years ago in our galaxy. So the light from this supernova was first observed in the year 1054, and this image shows what the afterglow looks like today, almost 1,000 years after that explosion was detected, and it's still pulsing with tremendous energy. When a supernova explodes, the outer layer of the star are blown away, but the core, which is the densest part at the very center of the star, can form either a neutron star or a black hole. A neutron star is a very extreme object. It has more mass than the sun, but it's squeezed into a space that's about the size of Manhattan. If you took a cubic centimeter or about a teaspoon of neutron star material and you brought it back to Earth, it would weigh about 100 billion tons, 1 cubic centimeter. A black hole is even more extreme. It is the densest object in existence. Now, as I mentioned previously, such massive explosions are rare because such massive stars are rare. So about 97% of the stars in our Milky Way galaxy will end up not as black holes or neutron stars, but as white dwarfs. As their cores collapse and they die, the outer layers of the star more or less serenely and calmly float off all around them. Now, this gas is then bombarded by hot ultraviolet radiation from the very hot core, and that results in really spectacular fireworks. The image here shows a planetary nebula called the Butterfly, for reasons that are obvious to anyone who knows what a butterfly looks like. It was taken with the Hubble Space Telescope. The gas here is estimated to be heated to a temperature of about 20,000 degrees Celsius, which is over 36,000 degrees Fahrenheit, just from the heat being released from the surface of the white dwarf. So they're a lot less explosive than supernovae, but planetary nebulae are still some of the most beautiful objects in the universe. So this gallery here is just a collection of planetary nebulae that were observed with a Hubble Space Telescope. And the 4 images all the way on the right also incorporate X-ray data, which is shown in pink, and the other colors mark the visible wavelengths. So whether it ends in a supernova or a planetary nebula, the outer layers of the star will be deposited back into the gas reservoirs of the galaxy. And out of that gas, new stars will be born. The gas that's recycled is enriched. That means it has more elements that are heavier than hydrogen because of the nuclear fusion inside the star that it came from, which then deposited that gas back into the interstellar medium. So previously, I've talked about black holes and neutron stars, and now I'd like to focus a little bit more on white dwarfs, which are pretty awesome in their own right, although they're not nearly as rare as black holes or neutron stars. Sir Arthur Eddington said it best back in 1927, and I quote, "We learn about the stars by receiving and interpreting the messages which their light brings to us. The message of the companion of Sirius, when it was decoded, ran, 'I am composed of material 3,000 times denser than anything you have ever come across. A ton of my material would be a little nugget that you could put in a matchbox. What reply can one make to such a message?' The reply which most of us made in 1914 was, 'Shut up, don't talk nonsense.'" For most normal stars, meaning those that are still burning hydrogen in their cores, which we call main sequence stars, their brightness is very strongly dependent on their temperature. Generally speaking, the more big and massive a star is, the hotter and brighter it will be. This relationship is illustrated in something we call a Hertzsprung-Russell diagram, or HR diagram for short, which is shown here on the right. Most of the stars you can see fall into the diagonal area that runs across the center of the image between the lower right and the upper left. But white dwarfs boggled astronomers because they completely defied this correlation. They were extremely hot, but also extremely faint. The only scenario in which this is possible is if the white dwarfs are condensed to an extremely small size, so that they must release their light at a very low rate because their surface area just doesn't have the capacity for a higher luminosity. The other exception to the main sequence you might have noticed is the giant star category in the upper right corner, which those stars are evolved stars, so they're not main sequence stars. This means that they've run out of hydrogen in their cores, and they're very close to dying. They're not quite dead yet because they either still have some other elements that they are able to burn in their cores for now, or they still have hydrogen to burn in their outer layers, even if it's not in their core. But that fuel isn't going to last much longer. These stars, they're called giants because they're physically expanded to a very large size, not because they're necessarily massive. And so these stars are very bright and very cold. So it's the opposite of a white dwarf, which is very hot and very low, has a very low brightness. Something even more mind-boggling about white dwarfs is that the more massive they are, the more compressed they become. So essentially you get an object that's about, has roughly the mass of the sun, but it's compressed to the size of the Earth. And an obvious consequence of that is that they are also extremely dense gravitational objects, not quite as much as neutron stars, but still very dense. So a cubic centimeter of white dwarf material would weigh only about a ton on Earth rather than 100 billion tons. Because of their immense heat, white dwarfs emit a lot of X-rays. They're barely visible in the optical light, which is the kind of radiation that we are capable of seeing with our eyes. But in X-rays, it's a completely different story. So on the left here is an image that was taken with NASA's Chandra X-ray telescope. And you can see in the X-ray band, Sirius B is actually brighter than Sirius A. So Sirius A is one of the brightest stars in the night sky. If you just go outside on a clear night, you look up into the sky, Sirius A is going to be one of the brightest stars that you see, if not the brightest. But Sirius B is not at all detectable with the naked eye, and you need a pretty strong telescope in order to be able to spot it at all. And it's much, much fainter than Sirius A in optical light, but not so in X-rays. In X-ray, Sirius B, which is the white dwarf, is much brighter than Sirius A, which is the regular live star. And again, in the optical image on the right, that's an image from the Hubble Space Telescope, and the bright object in the center, that's Sirius A, and the tiny little speck in the lower left quadrant, that's Sirius B, the white dwarf, and it's just barely detectable. So if you want to see a white dwarf, better look in the X-rays. There are a few different types of white dwarfs depending on their composition. So as I mentioned earlier, all stars start off by burning hydrogen into helium in their course. But what happens when they run out of hydrogen? There's going to be a period of core collapse, and the star's envelope will expand outwards. This is what we call the red giant phase. But if the star is massive enough, it will then start to burn the helium in its core into carbon. So a lot of white dwarfs are composed mainly of carbon. Now, after the star dies, once the outer layers float away, the white dwarf starts to cool, and as it cools, it crystallizes. As we know, when carbon is crystallized under conditions of immense temperature and pressure, it forms a diamond. And so, if you like diamonds, I hope it brings you joy to know that the sky is full of them, huge, gigantic ones just floating along in space. An isolated white dwarf will simply, continue to cool and crystallize for the rest of eternity, but very often stars don't live alone. They are coupled in a binary system. Because white dwarfs are so incredibly dense, they exert an enormous gravitational force on their surroundings. So when a white dwarf has a closely orbiting companion star, it's going to start siphoning off matter from the surface of the companion, which we then call a donor star. We call those binaries cataclysmic variables. Rolls right off the tongue. The material is going to pile up onto the surface of the white dwarf, where it's going to be heated to very high temperatures until it ignites a thermonuclear reaction, meaning it starts to fuse into helium. This will cause a massive explosion, which we call a nova, which can be 1,000,000 times as bright as the sun. Novae are so bright that we can sometimes observe them in distant galaxies, which is really great because it gives us a way to study the stellar populations and especially the distribution of binaries in those faraway galaxies that we otherwise wouldn't be able to see. Now, an equivalent process can happen also for black holes and neutron stars. Binaries are found throughout the Milky Way and other galaxies as well. They're pretty widespread. So when a black hole or a neutron star forms, often it will have a close companion. And in some cases, under certain conditions, it might even be able to capture a companion star after it forms. When that happens, if the companion star is close enough, the compact object might be able to cannibalize the donor star by siphoning off its mass. So the material is then going to form an accretion disk that will swirl around the compact object, meaning either the black hole or the neutron star, in an analogous process to what happens in cataclysmic variables where the compact object is a white dwarf. Accretion generally results in copious X-ray emission. Black holes are some of the brightest X-ray sources in our galaxy. Not isolated black holes, but black holes that have companion stars. And so I hope I've convinced you that dead stars are the coolest stars in existence. So I'm gonna leave you with that, but before I take your questions, I would like to take a moment to thank a few people, Ryan Galland, who organized this event, and all the other public talks this year, and my wonderful fellow grad students and other undergrad volunteers who volunteer their precious free time for those events. My awesome advisors, Chuck Haley, Kaya Mori, and Mike Shara, for all of their help and guidance. The National Science Foundation, of which I'm a graduate research fellow. Shout out to my dear friend Elke, my beautiful children, and of course little Mimi, who is the queen of my household, literally and figuratively. And finally, thank you again all for being here today. I'll take your questions now.
Thank you so much. That was a fantastic talk. So one more round of applause for Shifra.
Thank you.
You can, or I can.
I'm just going to go back to the beginning.
Cool. Okay. So, we'll be taking questions from the room, and also if you want to ask your questions anonymously, you don't want to ask them in person, we also have a tiny URL link, tinyurl.com/astro-questions-April 14th, April 14th, 1-4, to submit your questions. So we'll be going back and forth between the questions online and the questions in person. But I think, so I'm going to start by raffling off the, actually no, let's take a question and then I'll generate the random number to raffle off the first prize for the night. So, yeah. I think,
This is very naive, but when I understand X-rays, I think of them as seeing things that we can see with regular light, but they aren't able to see other things, like our flesh or the cavity. So how is it that the X-ray is able to see something better than another light? So if you could just explain that, thank you.
Sure. So that's a great question. So essentially, X-rays is just one part of the electromagnetic spectrum, which ranges from radio to microwave to infrared to visible light to ultraviolet to X-ray, and then the highest energy electromagnetic light is gamma rays. So it's not a question of X-rays are able to see things that we aren't. It's more a question of different objects emit light in different wavelengths. So a star, for example, take the Sirius AB system. Sirius A emits most of its light in the visible waveband, which is the light that our eyes are optimized to see. And that's a good thing, because that's also the light that's also where most of the sun's light is in. And we want to be able to detect that, obviously. And so Sirius A emits most of its light in visible light. That's why we are able to see it with the naked eye. We're able to see it with optical telescopes. Sirius B emits most of its light in X-rays, so we need an instrument that's designed to detect X-rays in order to observe it. And similarly, when you go to the doctor and you get an X-ray taken, the X-rays are able to penetrate certain parts of your body better than others, meaning the densest part of your body won't be penetrated, and that creates an X-ray image. But it's not that the X-ray sees things that visible light doesn't. It's that the X-rays produce an image that's different than that of visible light.
Okay. Before we take the next question, so our first raffle prize, to thank all of you for coming out here, is a ring with the black hole image of M87 on it that Shifra showed at the very beginning of her talk. And so that is going to Valerie Nadakwa. So, congratulations.
Can you raise your hand one more time?
And okay, so now we'll take a question from online. Since we do not know if Betelgeuse has gone supernova, how do we come to the assumption that it will die?
We know that Betelgeuse is going to die because all things must die, sadly. So it is with all living things, and so it is with stars. And we know that Betelgeuse is in a phase where it has evolved off the main sequence. And once that happens, a star's time is limited. Although, saying that a star's time is limited on a cosmological time scale is a little different than saying that, say, a human being's time is limited, because for a star, that means a star like Betelgeuse, it might live for another few tens of millions of years, and that's what we consider limited time, compared to the lifetime of the sun, which is about 10 billion years. So it's all relative. We don't think it has gone supernova, but again, we know that sooner or later that will happen, because it's inevitable. It's going to run out of fuel. There's a finite amount of fuel in its core, and once that runs out, the supernova will occur.
Okay, so another question.
So I think you mentioned either in full or in passing, I'm not sure, what elements are in white dwarf. I'm also curious, do any of those elements have a finite half-life? And either way, everything dies, you said? What about white dwarfs? What happens to them in a billion years?
Well, they crystallize, and certainly over timescales of 1 billion years, they'll still be out there. They'll take some time to cool, and they will continue to cool. Obviously, they start out extremely hot, and so the cooling process alone takes billions of years. But it's just something that, to the best of our knowledge, they'll just continue to cool into eternity, and nothing else will happen to them as long as it's an isolated white dwarf. Obviously, if it's in a binary system, as we said, then that's a whole other story.
And the elements?
Oh, well, the elements will just, again, if it's not in a binary, then there will be no more fusion, meaning whatever was there when it formed will stay there. No new elements will be formed. There will be some crystallization, as I said. There will be some sedimentation, which is a process in which the heaviest elements sink towards the center. But beyond that, things will be fairly static.
So, and then how many elements are there in a typical white dwarf?
So that depends. There are a few different kinds. Some white dwarfs are mostly composed of helium. A more common one is carbon oxygen. And the most massive ones are composed of carbon, oxygen, and neon. But that's about as heavy as it gets with white dwarfs.
Okay, another question online. How do we see so many different nebula shapes as planetary nebula?
I'm not sure is the question, why are the shapes so different from each other? Why do they not all look the same? Yeah, so, partly it's a matter of instrumentation. Historically, they've been called planetary nebulae because if you look at a planetary nebula with a, not the best, most modern telescope, it'll look sort of planet-like. And then the better the telescope, the more you're able to make out the details and the more the shape becomes clear. So with Hubble, for example, a lot of the planetary nebulae we observe have this kind of bimodal shape, sort of similar to the butterfly, where the center is sort of dusty, and then you have these two streams of gas coming out the two sides. So, you know, different stars, different environments, different compositions, different directions of collapse, all of these things can influence how a nebula will eventually turn out. Not to mention the surface temperature of the white dwarf at the center, which heats that gas and gives us all these brilliant colors.
Some more questions in the room? Okay, maybe so the second raffle is also featuring M87 black hole. That's the theme of tonight. And that goes to Ashwin Ramaswamy, who is...
All right, you have 3 seconds to claim the prize. 3, 2, 1.
Ashwin?
Oh, that's me.
Oh.
Can I also ask a question?
2 for the price of 1.
When a star collapses, does it into a neutron star or into a white dwarf or into a black hole, does it have the same gravitational effects, or just because it's denser, or because its mass should be the same or smaller?
Right. So nominally, gravity is determined primarily by the mass of the object. Where all three, white dwarfs, black holes, and neutron stars differ is, as you mentioned, their very extreme density. So the answer is, when you get very close to the surface, or in the case of a black hole, to the event horizon, there will be a difference because there will be other effects, just the extreme distortion in space-time. And the more dense the object is, the more extreme that distortion is. But when you get far away outside of the radius of influence, then that distortion becomes negligible, and the primary force is just the mass of the object. So for example, a white dwarf, the mass of the sun, if a planet or some other body isn't too close to it, then it'll behave the same way the sun might behave. But once you get too close, then that extra gravitational distortion comes in.
Okay, another online question. Do you have a favorite black hole? And if so, what is it?
Ooh, nope. I don't, sorry, I can't say. I'm I can't pick favorites. This is my work I'm talking about.
Fair enough. Another question in the room?
I'm going to come around the back.
Up there.
I guess while we're waiting. So somebody wants to hear more about the X-ray Jupiter stuff. And can you explain how that's different from an X-ray image of a white dwarf?
Oh, Jupiter is different than, well, pretty much any other object observed with X-rays in many ways. Most objects that we observe in X-rays are very, very far away. That has 2 main implications. One is that Jupiter is a lot harder to observe because it's constantly moving relative to us. When an object is super, super far away, it may be moving extremely fast, but because it's so far away, that barely registers when we point a telescope at it. And so Jupiter was much harder to observe. The other thing is that because those objects are so very far away, and we can still detect them here on Earth, that means they are X-ray bright. They emit a lot of X-rays. Whereas Jupiter, it emits a lot of X-rays, but nothing on the scale of those other energetic objects that we typically observe. Did that answer the question? Sorry, I forgot what the question was.
Hi, so I'm wondering if you could give us a little bit of context about the discovery, when black holes were actually discovered, why were they discovered at that moment, and is there anyone who can be credited with the discovery?
Okay, that's a pretty controversial topic, and I also have to admit, not my area of expertise, but I'll try to answer to the best of my knowledge. The person I personally credit most with the black hole is Chandrasekhar, who actually discovered the white dwarf mass limit. So what he discovered was that beyond a certain mass, a white dwarf cannot support itself and it will collapse further. That was, I believe, back in 1925, if I'm not mistaken. So it was only, and I should mention at the time he was basically laughed out of the room, even though he was 100% right. So it was only decades later that more of the theory was developed. I believe Oppenheimer was involved. He was probably among the chief, instigators who explored. Certainly among the people who postulated that black holes are just a natural consequence of general relativity. As far as naming them black holes, calling them black holes, that would have been Wheeler, whose first name escapes me at the moment. But again, it's like I said, it's controversial because apparently different people had the same idea at different times, and it's not entirely clear who was first. Sorry, I can't tell you more. There's a question.
So you told us like stars die and they become white dwarf or black holes.
Yeah.
And you also told us how some white dwarfs basically cool down and crystallize later on over time. But what becomes of the black hole over time? So do they kind of like keep on growing or something?
Yeah, so that's an excellent question. So a lot depends on the type of black hole and its environment. Where is it located? A black hole will eat anything that gets within its vicinity. So if it's in a neighborhood where it's being fed, it will continue to grow. Beyond that, say you have an isolated black hole and it's not accreting any matter, over many, many billions of years, it will start to leak. It's a phenomenon called Hawking radiation. And you might ask, well, how can anything leak out of a black hole or evaporate, which is actually the term that we use? How can anything evaporate out of a black hole when nothing can get beyond the event horizon? And it's a little bit of an evolved answer. I'd be happy to chat about you afterwards, but the basics of it is that if there's a pair of particles, a virtual pair of particles that are created right at the event horizon, one of them might escape and the other might fall back into the black hole, in which case the particle that's escaped, we call that Hawking radiation. And so eventually, over many, many billions of years, an isolated black hole might evaporate. Again, a lot of this is really strictly theoretical, considering that most of this is stuff that we don't have the capability to observe.
Okay, well, I guess one more, another online question. Can you briefly explain what brown dwarfs are?
Okay. Brown dwarfs are distinct from white dwarfs. Brown dwarfs are essentially failed stars. So as I mentioned in my talk, in order for a star to be considered a star, it has to be burning hydrogen in its core. It has to be taking hydrogen, turning it into helium. A brown dwarf is an object that is not quite hot or massive or dense enough to do that. It is, however, able to turn hydrogen into deuterium, which is a form of hydrogen that also has a neutron as opposed to just a proton in its nucleus. And so it's sort of in the space between a planet and a star. It'll be more massive, more energetic than a planet, but hasn't quite made the cut to become a star. So definitely different from white dwarfs, although it does have one thing in common, in that it is also something we call degenerate, meaning that weird property of white dwarfs, where the more massive they are, the more compact they are. That's something that is relevant to actually. I'm not sure if it works quite the same way, but they're both degenerate. That's sorry, also not my area of expertise.
They used to compare black holes to like a sewer drain or water drain. The water goes down. into another dimension, supposedly. Would that be the source for dark energy, dark matter?
It's unlikely. We've come close to ruling it out as a possibility. That's the short answer.
Hi there. So first I wanted to say excellent talk. Thank you so much. Appreciate it. I have now two questions. First, you may have already answered this because you mentioned Jupiter, but I recall previously watching a documentary saying that Jupiter was a failed star at some point. I'd love to know more if that is in fact true. And the second question is completely unrelated, but in your professional opinion, what is the best sci-fi movie that accurately incorporates astronomy?
Okay, well, question one is easy. Question one is very easy. So Jupiter, in fact, is, if it were any massive than it is now, meaning 10 to 100 times as massive as it is, it would be a star. So in that sense, I guess you could say that Jupiter is a failed star. It's not quite massive enough to be a star, but it's close. It's right up there, and it's almost like a mini solar system within itself. So yes, Jupiter, super cool, my favorite planet. I wish I could tell you what my favorite sci-fi movie is. Unfortunately, that is so far outside of my area of expertise. As Ryan mentioned, I was raised in a very insular Orthodox environment, and I wasn't exposed to any movies or outside media generally, so I still have a lot of catching up to do, so I'm sorry I can't offer a recommendation.
Okay. So before we move on to other questions, like I said, one piece of bad news and two pieces of good news. The bad news, it's a little too cloudy to observe tonight, unfortunately. But next time it will be there. Yeah, if we keep getting losses, eventually we're going to win, and that's next time. The good news, well, first piece of good news is that now we have plenty of time to ask Shifra more questions. She can go for as long as she feels comfortable asking questions or answer questions. The second piece of good news is that I can wait longer to announce the raffle winner for our last prize, which is a black hole bag with an accurate, I guess, what do you call it, a corona or like photon ring, accurate color on the inside. But I'll announce that in a little bit. And also, this raffle is very effective. I appreciate that you're very easily bribed into giving me more information. Because since I started raffling stuff off, I've gotten like 30 or so more assignments. So thank you for that. But another online question. Can white dwarfs become black holes or neutron stars later in life?
Very good question. Not if they're isolated. However, if you have two white dwarfs in a binary system orbiting each other, and they merge, then they might form into a neutron star or even a black hole if each of them is right at the mass limit. So it's possible, but not common, and only under very specific conditions.
Coming up to the back. You mentioned moving objects. How important is orientation or locality when observing something that's moving or constantly moving?
Yeah, so again, I should mention that Jupiter is the only such object that I've ever been involved in observing. So I'm not sure if I'm the best person to answer this question, but essentially you have to keep adjusting your telescope to point at it. And so, yeah, sorry, I don't know. That's all I know, that if you have an object that's moving, you just have to keep adjusting your pointing direction so that you can keep it in your field of view. Sorry.
Hello. Could you talk a little bit about the information paradox in black holes? Because it's something I have a hard time sort of understanding.
Yeah, me too. So the information paradox is essentially, like I said, there are only those three or rather two hairs in a black hole, those two quantities that tell us everything there is to know about a black hole, meaning all the information about the black hole from the time it was formed, except for these two parameters, has gotten lost. And so that's the information paradox. And I think I'm as puzzled as everyone else by it.
And a question online. Oh, go ahead. How are the ages of black holes determined, and what is the oldest black hole that we know of?
Yeah, very good question. I think the short answer is if you have an isolated black hole in the middle of nowhere, there really isn't a good way of dating it. The only way I can think of on how to date a black hole is if it's embedded within a cluster of other stars or if it's in a binary system. And then the stars around it or the other star in the binary can give you clues as to how old the black hole is. Otherwise, well, if it's a supermassive black hole, then again, the galaxy that it's in will tell you approximately how old it is. But a stellar mass black hole, again, you need other information in order to be able to figure that out.
You had a slide which showed the nuclear fission outward force and the inner gravitational force, which keeps a star, a star's structure, its structure. In theory, talking on like level scales, is this gravitational collapse possible on a galactic scale? You mentioned like a binary star system in which under very specific conditions it's possible, but
to in-spiral, yes.
Yeah.
Right. So you're asking if the gravitational collapse can happen for a galaxy rather than that's a very good question. I don't know. Honestly, it's a little difficult to picture a scenario in which that would happen because typically when things collapse or spiral inward, there's some sort of dynamical change going on that's causing that loss of energy. In a collapsing star, it's the fact that nuclear fusion has stopped. In an inspiraling binary, there's usually some kind of friction or shear or other effect that causes it to lose angular momentum and spiral inwards. So for an entire galaxy, it's hard for me to imagine a scenario where that would apply to, say, a whole disk of stars.
Once you finish your PhD thesis soon, we hope, do you have other topics in mind that you'll want to research? And if so, what are they?
Well, how much time do you have? Yeah, well, black holes are certainly my favorite, but there are a lot of topics that interest me, chiefly among them nova eruptions, which I've also studied in the past. I'm also interested in cosmology, particularly studying the dark matter mass distributions in galaxies. Yeah, it's a big world out there.
I think since some people are starting to trickle away, I guess, I'll announce the final raffle winner, and that is Palin Lee. Where's Palin? Oh. And in the meantime, another online question. Can binary stars that create recurrent nova live forever?
Forever, no. Essentially, in order for recurrent nova to happen, a lot of the mass of the donor has to be siphoned off onto the white dwarf. And so the donor is just going to be whittled away very, very quickly. Other things might happen, like maybe that donor could be ejected from the system, and maybe a new donor could even be captured if it's in a very dense stellar cluster. That's a possibility. So the white dwarf might live to see another day, but the donor won't have such a happy ending.
Great talk. What do you expect the Webb telescope will reveal that that you hope or expect that hasn't been revealed so far?
Yeah. Again, my area of expertise is in X-rays, and JWST is in infrared, but it is an incredible instrument. Personally, I'm hoping that it'll help us observe stellar spectra and stellar motions to such fine detail that we'll be able to discover black holes that are so far away that we currently can't see them, but we'll be able to detect them from the motions of the stars around them, which I think would be really awesome. And another major thing that's coming out of JWST is that we are seeing galaxies formed at ages earlier than we thought possible. And that's given us a whole new window of information into just the broader cosmological paradigm, just how things formed and came to be the way they are. And there's really a lot of incredible, groundbreaking stuff coming out of there.
So then, okay, another question. How do we get the really massive black holes that are 100 times the mass of the sun?
Yeah, so that would be an intermediate mass black hole, and it's not a question that we necessarily know the answer to, although there are plenty of theories. I believe, if I remember correctly, only a handful, or maybe just one intermediate mass black hole was ever unequivocally confirmed. So we know that they're out there, but they're extremely difficult to observe. One way you can get a 100 solar mass black hole is through repeated mergers, meaning if you have, say you have two 20 solar mass black holes that merge together, they form a 40 solar mass black hole, which might then merge together with another 40 solar mass black hole, and so on. And so each of these mergers would be extremely rare and extremely unlikely. So getting 100 solar mass black holes specifically would be very, very difficult, but maybe not impossible. Or, this is an area of ongoing active research.
Hi, 25 years ago, I took a cosmology class, maybe even in this room, don't remember. Only thing I remember from that class was the measurements they had at that time was so rudimentary that the professor kind of half-jokingly said, sometimes they just take pi as 1 because it really wouldn't matter too much in terms of the result. Have things improved since then?
So that depends on the area of research. So when you say pi is 1, that's, does anyone know the spherical cow joke? Essentially, physicists and astrophysicists are infamous for, rounding off. Well, as long as it's correct to within an order of magnitude, we don't really care, and oftentimes it doesn't matter. Meaning, as long as we can figure something out to the nearest power of 10, we don't necessarily always need to know more than that. So it depends on the science. A lot has improved over the last 25 years. There are many, many things that we know now that we didn't then. But there are still some areas where we're, sort of guessing, sort of trying to feel out what the limits are and what the practical range is. And we're always learning, and that's just what science is. We're always trying to improve and trying to incorporate new information, and trying to guess as best we can the things that we don't know yet based on the information that we have.
What's a spherical cow joke?
Well, I'm not very good at telling jokes, but do you want to tell her, Ryan?
You can try.
I can try, but well, you've been warned. So essentially, it's a riff on how physicists just estimate everything very roughly. So a group of people are presented with a challenge of figuring out the volume of a cow. And, so there's a mathematician who does a bunch of very complicated calculations and comes up with a number, and the engineer who, I think, just dunks the cow in a tank of water and sees how much the water level increases. And then you ask the physicist, and he says, well, just assume that the cow is a sphere.
That was good to know. Okay. Now this is a very difficult question from online. Are you looking to adopt Mimi the Queen?
Probably.
Another question?
Thanks, Shifra. I had a question about why white dwarfs emit X-ray energy versus live stars emitting visible energy, energy in the visible light spectrum, if they're still undergoing the same fundamental, nuclear fusion reaction of hydrogen to helium. Why that light emitted is different?
Right. So essentially, white dwarfs are hotter than most stars that are still active, even though they no longer have any nuclear fusion going on in their cores. And that's a consequence of just preservation of energy, because when that white dwarf collapses, you have something that was really big and it collapsed into a tiny point. So all that gravitational potential energy that was lost, well, it wasn't lost, it's been transported into thermal energy. So when it first collapses, it becomes extremely, extremely hot, hotter than most stars. And that heat takes some time to dissipate. And that's why it actually emits in X-rays more than in the visible band. Although in the visible band, it may be barely detectable because of the very high temperature, the light that it emits peaks in the X-ray band.
I think we'll do one more online question, and then maybe a few more in person. Okay, first, I should have announced this earlier, but we also do have a feedback form. There's unfortunately no raffle to go along with that. Maybe we'll figure something out. But yeah, as you're on your way out, make sure to fill out that tinyurl.com/astrofeedback, because that's also very valuable to us. But okay, so now the last online question. Actually, well, I just got another online question. So I guess maybe second to last. So is the fate of our universe destined to become a massive black hole?
I can't see why it would. I don't think so. Maybe.
Question. So how is it that white dwarfs, neutron stars, can be so incredibly dense? And then follow-up question, how is it possible that a black hole could be an infinitely small point? Like, how could all of the matter occupy the same space?
Well, the short answer is it's beyond our comprehension, really, or beyond what we can visualize, really. A black hole being essentially a singularity, or a point that's where the density is infinite and it takes up no space at all right at the center there. Although the event horizon, I should mention, very much does take up space. It's just the singularity at the center that has zero volume. Yeah, so that's not something that we can really conceptualize. As for white dwarfs and neutron stars, it's incredibly intense. It's just, you just have to imagine a pressure that's big enough to crush it into that tiny, tiny volume.
Okay, so I think the last online question. So is there a theoretical limit on how cool a white dwarf could be at this point in time? And if so, have we found any white dwarfs close to that theoretical?
So I don't think it's so much a theoretical limit on how cool a white dwarf can be. I think it's more of a limit on how cool a white dwarf can be, and we'd still be able to detect it. Because theoretically, if a white dwarf could cool to 0 degrees Kelvin, but long before it hits that point, it would be all but invisible to us. And so I don't know off the top of my head the coolest white dwarf ever detected, but I do remember that it was one that was theorized to have already crystallized its core, and so it was theorized to be, there were all these pictures of a diamond peeking out of a stellar crust. I don't know if that's what it actually looks like. Nobody does. Actually, I'm pretty sure it doesn't look quite like that, but should still be pretty cool. Yeah.
Maybe one more question.
The supernova that was observed by Chinese astronomers centuries ago, that they saw it in the daytime for a whole week.
Yes.
You know what year that was? And what
Was that the crab?
Yeah.
So that was in 1064, I think I have it. 54, I have it in here somewhere. Let's see. This one right here. Yeah, 1054. That was the year.
What was the supernova?
So it was a very massive star that exploded, and it left behind a pulsar, which is a type of neutron star that spins very, very fast.
What do you call it today?
The Crab Nebula.
Crab Nebula. Was there a European equivalent? European astronomers observed it too?
I don't think so, because it may not have been observable at those latitudes. So I don't know. Yeah, I'm not sure. It may not have been visible to them.
Okay. One last huge round of applause for Shifra.
Thank you.
Again, thank you all so much for coming. This is fantastic attendance. Maybe even better than our event with David Helfand 2 weeks ago. So hopefully we have even better attendance in 2 weeks on April 28th. Hopefully fill up the entire auditorium. So yeah, if you have any more questions, you can come up and ask us here. Yeah, thank you.
So I'd like to. So Jupiter is not a brown dwarf?
It is not. No, it's close to being one. If it were only just a little bit more massive, but it didn't
So it's the
quite
mass.
make
Wow.
it. Yeah.
So now, is there a thing called a red dwarf?
Yes. So a
But
red.
it's not on the Hertzsprung-Russell diagram.
It should be. I think a red dwarf is a main sequence star. It's among the faintest stars. So it's among the smallest, faintest stars.
I have it here.
But it's just a very small, very faint star.
I've been arguing about that, and I had not seen a red dwarf.
Right. So they wouldn't